Okay, hi everyone. Welcome back. That from our musical interlude break. That was great. It now gives me pardon me, great pleasure to introduce our third speaker of the workshop. We're very lucky to have Arne Sieverling with us from Realtime Robotics. One of the things that we thought was very important, as Nathan just discussed, actually, is to incorporate a strong industrial presence in the workshop, right? Because we're actually very interested in seeing what industry is doing in this area and not limiting ourselves just to academia, because really it'll be industry that's ultimately going to deploy and sell these power on and go systems. All right, so just a little bit about Arne. He's a senior robotics engineer, as I said, at Realtime Robotics, which is based in Boston. They're a startup that's actually bringing accelerated motion planning into industrial robotics applications. So really exciting stuff, really cutting edge. Arne's work at Realtime actually focuses on sampling-based planning, real-time trajectory generation, and the system architecture actually that's required to operate a very wide variety of industrial manipulators in a unified way. So Arne actually received his PhD from the Robotics and Biology Lab that many people are familiar with at the Technical University of Berlin, supervised by Professor Oliver Brock. And during his PhD, he primarily worked on planning and control algorithms for mobile manipulators, which we're very fond of as well, using both vision and tactile sensing. And just as a highlight, in 2015, he was actually part of the team that won the Amazon Picking Challenge with a mobile manipulator and a vacuum cleaner. So, all right, with that, I'm delighted to hand it over to Arne, and we'll wait to hear the exciting things he has to tell us. Thanks, Arne. Take it away.
Yeah, thanks for the nice introduction. Can you hear me and can you see my slides?
Looks and sounds great.
Perfect. Thanks for inviting me to this talk. I'm here to give a bit of an industrial perspective. We are about 4-year-old startup in the field of motion planning, and we're trying to get research or current edge research in motion planning into industrial applications. And initially, whenever I'm at these conferences, industrial automation is always kind of in the area of, okay, we solved that problem, let's look at harder topics. And in a way, it's true that industrial automation is a big success story. I mean, 2020, there are about 550,000 new robots going out into the world. And this number is increasing on average about 40% every year. But however, if you look at the bigger picture, there's still over 1 billion people employed for the dynamic motor skills, for the skills in manipulation, basically. And robots is just a small, tiny fraction of that workforce. It's less than 0.3%. And the number of tasks that could be automated is probably and obviously much higher than that. So it's still largely a cost factor that inhibits robots from being used more widely. And if you now look at the actual deployment cost of classical automation work cell, let's say a cell doing a step in building a car, the majority of that is actually integration. It's people that write the software, write the robot programs to solve a very specific task. So the normal workflow of these applications this is done by companies that are called integrators, and they are specialized in just that, getting these robots together. They design the environment and they create some high-level task plans. And then they create motion plans, usually manually by teach and repeat, just moving the robots into positions. Then they get those taught positions onto the robot program controller and test and iterate. And really the last steps here, this is more like an iterative process, because the real world usually is different than the designed environment you started out with. So these people usually go into the factories, run the plans at low speed, check for potential collisions, adapt the plans. And this is all a very time-consuming process, and it also requires a lot of specialist knowledge. Every industrial robot has its own operating language. So this all adds up to this really high costs for integrating these work cells. So this is not really power on and go. You could say once the system is set up, it's power on and go, you press a button and it mostly works because it's doing all the same things over and over again. But the process to go there is far from power on and go. It's very costly, it's very involved. And now, if you would ask us researchers, okay, how would that process look optimally? It would probably just be a simple, you design the environment, you specify the task. Then there's some system that optimizes how many robots do you need, where to place them, in which order, and how should they move. And then deployment should also be smarter than just get an engineer there and adapt until it works. It should be, the robots should be aware of the surroundings. They should perceive changes in the world from what they started up with, and they should adapt their plans automatically. And I'm going to mostly focus on step 3 here. However, at RGR, our bigger picture is to work on that whole pipeline and making the setup and the running these work cells a much easier process using all the years of robotics research. And yeah, a key to deploying these robots is to making them more reactive and more adaptive to changes in the environment. So they need to be able to perceive the environment. They need to be able to instantaneously adapt the plans to changes. And this instantaneously is important. Planning must basically be latency free. If planning takes half a second and every robot in your production line needs half a second every time something changes, this just adds up. So planning must basically be instantaneously. Deployment should be hardware independent. You shouldn't not need to learn a different programming language for every new robot you bring into your scene. And especially if there's humans in around and you plan to move your robots close to humans, it needs to be safe. It needs to be provably safe because every industrial application needs to be certified. And if you cannot prove that you're not hurting anyone, it's probably of no use in industry. So the idea of real-time robotics basically started with an RSS paper, and that is also 4 years ago. It's called Robot Motion Planning on a Chip, and I'll walk you quickly through the basics of that one. So it was back then a team of researchers at Duke Robotics, and they came up with an idea to extremely parallelize the collision checking part of robot motion planning. So the general idea is based on probabilistic roadmaps, and usually these roadmaps work. You sample random configurations, and then you incrementally build this network of collision-free motions until you find the network is dense enough that you find a path from start to goal. And in the RSS paper back then, this process is split up in 2 steps. And the first step is offline, and that is we create and construct a really dense, large roadmap, and then we just aggressively pre-compute all the swept volumes. So these are basically the volumes that the robot will sweep through when it does a specific motion. And we just discretize this and save these. And then online, what you do is you just compare the sensor data to the pre-computed swap volumes. So this is basically like a logical comparison for any edge in my roadmap. Do I have any voxels that collide with the voxels I'm getting from a point cloud, for example? And you do that online, the comparison. So red are now obstacles, new obstacles you didn't have initially. These obstacles would invalidate a few motions, and then in the remaining graph, you would do a short sparse query to find the goal. Now, the idea is to make this logical check, this voxel comparison. Basically, it's a logical expression, and you can write it down, and then you can bake it in hardware. You basically have an FPGA, which only purpose is to evaluate this logical expression for huge roadmaps. We're talking about up to 1 million edges at once. So this is, the idea is really to have a dedicated hardware to do this collision checking fast and then exploit this parallelization as fast as you can. And this gives you orders of magnitude faster collision checking. So here you see the latency you would get from this approach compared to the size of the roadmap. And as long as you have enough memory on your hardware, the hardware accelerated approach actually checks the whole roadmap in constant time. While if you would implement the same on CPUs or GPUs, you will get speedups, but you're still orders of magnitude faster, and it's dependent on the size of the roadmap. And this is really interesting for industrial applications because it basically makes motion planning a deterministic process. So in a given very short time budget, I can tell you for all of a pre-specified set of motions, which ones are free and which ones are colliding. And this allows basically to trigger planning as part of a feedback loop. For every new sensor data you get, you can completely start to plan from scratch because it's such a short operation, basically. So the remaining question is, okay, we need to pre-specify these roadmaps. They need to be known in advance. How can they be created? And there's a lot of research and how to sample to get good roadmaps. We actually ended up for a much more user-driven approach. And the idea here is that robot programmers usually have a pretty good idea about where their robot is going to move and which regions of the space they're interested in. So this is our software toolkit, which basically is like a graphical programming tool that allows users to specify regions they're interested in. For example, here on the table, you have denser regions with denser samples, and then you maybe have a few wire points because you want to do the task in different ways. And this toolkit then automatically creates connections. So it starts local motion planning problems to find connections between these points and computes all these web volumes. And this is all happening offline before you actually run the application. So this is a way basically to get the robot programmer's knowledge about the task and bake it into our hardware. And so the robot has different options to do a task, but it will still be among a very defined set of motions. This is a bit different than motion planners that gives the robot complete freedom. So this is basically, from this idea came our core technology, and the same idea is still in the product we sell now. And this is basically two products here. On the left side, it's what we call the real-time controller. It's an industrial PC with exactly that custom motion planning hardware inside. It comes together with a software toolkit to create these roadmaps graphically. And on the right side, it's what we call rapid sense. That's the spatial perception part of all that. So now that you can plan amazingly fast, you also need something that gives you good enough sensor data at high update rates so that you can actually make use of that and adapt to plans. But first I want to start with a real world application that actually doesn't need the right half. It just requires no external perception. And the idea here is you take our industrial PC and connect it to industrial robots. So we basically have interfaces to all of the common industrial robot manufacturers out there. So here's a list. These are the biggest ones out there. So I'm pretty proud of this because this is a lot of effort we just put into making our stuff work independent of the robot, which basically makes the kind of robot you want to use plug and play. And applications we're tackling are things like this: industrial robots on a tight space doing complex tasks, and all these robots must avoid each other, and you must guarantee that they stay collision-free. The idea now is to use this online planning for multi-robot planning. And what you basically do is you pre-compute this web volume for all your motions, just like before. And then whenever a robot moves, they just reserve the voxels of this web volume for the motion they want to do. And these volumes are then obstacles for all other robots. So the other robots then just plan the path around the motions the other robots would do. How does this look like? This is a simple toy example, basically stress testing this approach. You see 3 or 4 robots running at full speed, and they basically randomly choose a point in their workspace. And then if there's a collision-free path to go there without colliding with the other robots, they just go there. And if there's no collision-free path, they pick the next point. So all of these robots are just running a simple 3-line script, and all the higher level coordination, there's no single coordinator running here. They're basically all acting individually in the space of collision-free motions. Here's the same, a bit slower, and on the left you see the volumes that all of these robots block in their motions. And what you see here is that the planning time, the time for the robots to make decisions, is basically non-visible here. We plan within milliseconds, and this is crucial to get such a good performance here. This is the same idea in a bit more industrial setting. An integrator implemented this for a Japanese trade show. Basically, 2 robots picking and placing. And at the same time, they avoid each other. And coming full circle, this is a very valuable technology for industry, and we are cooperating with Siemens. They're the leader for industrial simulation of these manufacturing work cells. So there's a software called Siemens Process Simulate, and this is the standard for setting up these work cells. And our technology is on the way of becoming basically a plugin to the simulation environment. And these integrators now can use our technology to very quickly come up with plans where all the different robots avoid each other. And this was also already used by integrators who could reduce the time-consuming task of programming and defining zones where a robot cannot be at the same time. It's usually a pretty involved process, and they could reduce all that by up to 70%. Okay, so on the other product is what we call Rapid Sense, and that is concerned with actually generating data so that robots can perceive changes in the real world, and actually use the perception of the real world to adapt their plans instantaneously. And our system is based on a number of RGBD cameras. So we take up to 8 real-sense cameras here and merge the data to receive a really dense and good high-resolution point cloud. The tricky part here is usually always calibration. Calibration is a painful process. What we can do here is really exploit that we have robots in a work cell. So the calibration becomes almost fully autonomous. It just requires to mount a fiducial plate to the robot. And then our planner comes up with good viewing positions and also with collision-free motions between these viewing positions. And here you see the data these sensors generate. Here you see the system in action. You see it's running still at the original frame rate of the maximum frame rate of 90 frames per second, combining the data of 8 3D sensors. And setup and calibration, as I said, is mostly automated. So the only input needed is the first initial view of the fiducial plate, and everything else will happen autonomously. And it's able to detect free, blocked, and also occluded space, because you need to reason about occlusions. Otherwise, you might collide with things you're not seeing. A technical challenge here is really filtering out first the robot, but also things that are not really well modeled beforehand. For example, every industrial robot usually has large cables attached to it, and these are really, really hard to model analytically, but you need to find a way to filter them out of the voxel stream. Otherwise, the robot will see itself as an obstacle. Yeah, this data is sent to our online planning system, and at this 90 frames per second, the system can also come up with a new collision-free motion plan continuously. So here's a video of the system in action. It's combining both the multi-robot capabilities and also the spatial perception capabilities If your video is very laggy, you can also go to our webpage rdr.ai and basically see the same videos because the robots are moving a bit faster. So you see that the planning system allows to change target location, for example, instantaneously, and there's no visible planning time. And also, if you add obstacles, the perception system picks it up instantaneously, and the planning system immediately finds a way around. So we're planning at 90 frames per second here. And the next video that's coming also shows a bit about the reactivity of the system. So you can try to make it crash. It's really hard. The robot perceives obstacles fast and immediately stops. You also see that if the roadmap contains enough options for a robot to move around an obstacle, it will immediately move around. So this concludes our view at Realtime Robotics about what I today call power on and go automation, which is basically this process of not fine-tuning, not orchestrating motions individually, but using motion planning technology, using real-time motion planning technology to, on the fly, come up with collision-free and good motions. And yeah, the process here is building and configuring robot work cells graphically. There's a large part of optimization, and this is basically the question of, okay, where to place robots, how, in which order should they do tasks, and there is exciting stuff from us coming soon, so keep watching out for that. And then the question of, okay, how can we deploy these robot cells in a more robust way and let them automatically adapt to changing environments? And yeah, our tool of choice, real-time motion planning, has helped to make these things really reactive and really robust and fast. Yeah, and with that, I would like to thank you and hear your questions.
Right, wonderful. Thank you, Arne. That was fantastic. Extremely interesting stuff. So we got a couple of excellent questions in the chat that we can ask you. We have a few minutes for answers as well. So we have a question from our next speaker, actually, who's up immediately after you. The question is regarding the design of specialized hardware, which is, it's known to be a very time-consuming effort. And in particular requires a team with heterogeneous expertise. So you need someone who can do the chip design, the hardware design, algorithms, integration, all of these pieces together. So if you have an opinion about the role of academia, could you share that opinion? Do you think, what role would academia play in those pieces? Or do you think that a startup or a company environment is really the place to develop specialized hardware robotics because it requires this multidisciplinary and interdisciplinary team?
In our case, first off, I think it's not that easy to just take a robotic system and then say, I want specialized hardware for this and that, and then just expect the speed ups we see here, for example. So our startup, the idea of that is only possible because there was this interdisciplinary team of hardware and software professors and students doing their PhD thesis on this and finding what exactly is it that we want to bake into hardware and parallelize a lot. So coming up with the first prototype, I think, can only happen in a research context and will not happen just like that, because there are a lot of things that you could do, but I think finding out what you want to do and prototyping that is definitely something that should happen in research and requires probably cooperation of robotics people and hardware people.
Okay, interesting, very interesting take. Absolutely. Okay, we have a couple. Actually, we probably have time for three. So let's try for three potentially. I'm going to ask one from another one of our speakers. Can you achieve, this is from Stefan Ludmega this morning. Arne, can you achieve 100% safe interaction with humans thanks to the online depth sensing that you have available? And are you able to do that even given their motion in front of the robot or around the robot?
Yeah, so we have to. We can do that. So if you want to run these kind of systems in an actual industrial application, you need to get it certified. And certification basically means you prove that the system is fault tolerant and will hurt no humans around. So and this is a lot of work. This means all sensing must be redundant, and you need to basically rewrite everything from scratch, keeping absolute safety in mind. And there are standards for that exactly describe how your system must look so that it's provably safe. So we're on the way of doing that. We want to get this system certified so that it basically becomes a system that is provably safe and will stop before it hits a human.
Okay, all right. I will ask one more quickly from you, which is another one from our next speaker, but also something that I was going to ask you about. It's an issue about scaling the systems, and I was also going to ask in the multi-robot context. So could the systems be scaled up from non-fixed base to non-fixed base systems to mobile platforms, for example, like moving in, say, a large workspace like an entire building? And if you have multiple robots interacting, is there any way in your current system to guarantee that you get near optimal plans for multiple robots that may be moving? That's sort of kind of two questions, so my apologies.
So the first one, you could treat, or we're working on initial prototypes to get our system running on mobile basis. So in general, there's nothing that speaks against using these technologies with the extra 3 degrees of freedom. Yeah, it needs to be seen if you can boil the things your mobile manipulator should do down to a roadmap like that. But what you easily can do is move a base around, and then basically it's just the changing environment that the planner needs to deal with. So this is definitely a feasible solution also for mobile manipulation systems. And the second question, oh, sorry, I need to hear that again.
Oh, it's just whether you can, if you have multi-robot systems and they're not maybe in direct communication, for example, in the video you showed, can you get an optimal or near optimal trajectories for those systems? Or is it just best plan first type of, a best plan first type of approach such that collision is avoided?
So you can seed the algorithm. Whatever you do offline, you can try to be optimal, and you can basically seed it with motions that are almost optimal. But at runtime, you basically need to instantaneously decide what to do. So with the latencies we're talking about here, if you want to plan in a few milliseconds, there's no time to go close to an optimal solution, especially in a multi-robot setting. So what we're doing here is not optimal, but we're talking about motions that maybe take half a second in maximum. Usually the gain of not wasting time to plan.
Right. So you lose more by...
Yeah, by trying to be optimal and waiting 200 milliseconds until you have your optimal solution.
Right. Yeah.
Because these robots are fast, and you don't have a lot of room to plan.
Right. So actually, it's very interesting that you're saying it's actually worse to. Sometimes the optimal, the perfect is the enemy of the good, right? As they say, like you certainly you don't need that optimal plan. You just need something that will work, and it'll work quickly, and you'll wait too long for the optimal solution. So fascinating.
So I think in our paradigm, what you definitely can do is offline, you come up with optimal solutions for some tasks, and then online you choose the right one.
All right, fantastic. Okay, well, I think that's what we have for questions, and we're actually bang on time. So we will thank the speaker one more time, everyone. Thanks to I'll do my little clap. Thanks to Arne very much. That was a fantastic talk.